Okay, 3, 2, 1. We're recording. All right, so we learned the mean value theorem yesterday for integrals, which is related to the average value, right? The average value is the integral divided by the width, and it's the way to give you the average function value for continuous functions, right? So in this case, this is what we ended with yesterday. I wanted to figure out what the average y value of this parabola was from -1 to 2, right? So how many y values do I actually have on this interval from -1 to 2? Infinitely many, right? And they all exist through a continuum. So I can't add up infinitely many y values and divide by infinity. That would be what we call the arithmetic mean. That's good for discrete data. So instead, we find the area of the entire region from -1 to 2, which was in green, and we divide it by the width from -1 to 2, which is 3 units, and that gives us the average y value, which we found to be 2. Okay, so the geometric meaning of that again is if I use a height that is the average value, and again, the theorem guarantees that it occurs at least once on the closed interval. We got it occurring twice, once at the left endpoint and one's at the interior. But the rectangle then on the same interval, whose height is that same y value all the way across, gives you a region that's equal in area or equal in accumulation to the area under the curve. And it is not drawn to scale, right? Because what that would imply then is this vertically hatched area and this horizontally hatched area would be equal, right? So it's not really drawn to scale, but the numbers don't lie, okay? So if we're trying to find the x value where the average value exists, we do the integral, we divide it by the width, we find the average value, and then we set it back equal to the original function to find the x value. That's what we did yesterday. Now, a lot of the times, these show up as free response questions, as I mentioned, and you'll be asked to interpret it. So if you see 1 over a number out in front of an integral, it's probably the average value. And a lot of times it shows up in, data points. So even though data points are discrete values, if they come from continuous functions, we can still approximate the average by what I call the density method. So here's what example 15 says. The table below gives values for a continuous function. That's important. Use the values given, find the arithmetic mean, and then use the trapezoidal approximation with 6 subintervals to approximate or estimate the average value, okay? So the arithmetic mean, I don't think I'm going to take the time to do that, but the arithmetic mean would essentially be 42 plus 38 plus 31 plus 29 plus 35 plus 48 plus 60, get the aggregate total, and then divide by 7, which is how many y values there are, right? So like if these were your grades in this class, 42, 38, 31, 29, 35, 48, 60, first of all, I'd ask you to come in tutorials more often, right? But I would find your average by dividing by 7. And that would be a good way to do it because your grades in this class don't come from a continuous function. They are discrete data points. But as we were talking about, like at this temperature, we know that in between, the temperature had to exist by the IVT. It had to be everything in between, right? So I'm just going to do the trapezoidal method. So remember the first step when you're doing trapezoidal methods, whether it's to find average values, which involve the integral, or just straight up approximations of the integral, we're going to calculate the intervals. So the first step is to look at the interval in question. It is from 20 to 50, and our data points then go from 20 to 50. So you might need to read carefully. It is 2022 after all, and if this interval had been from 30 to 50, you would have to know to just ignore the first 2 data points, right? So that's kind of one of those trickeration things they might be fooling these days, right? Trying to increase your awareness. All right, so now let's calculate the width. From 20 to 25 is 5 units, 25 to 30 is 5. Don't assume, right? But it looks like it's going to be 5 all the way across. Now that, because it's a uniform delta x, we can expedite the process. And however many delta x's that we compute, that's how the maximum number of subintervals we can use for left endpoint, right endpoint, and trapezoid. We could do a midpoint here, but we'd have to go every other interval. All right, so that's 1, 2, 3, 4, 5, 6, and that's what it asks us to use. So we're going to use all of them. So here's what we're going to say. We're going to say the average value, or you could say the average f of x value, or the average of f of x, if you want to use the passive voice. I'm not about the passive voice. All right, so it's going to be the integral divided by the width, But hey, let's set it up first. It's going to be the integral from, let me come back here and change my region, interval back to 20 to 50 of f of x dx, right? That's the integral. And then divided by the width, which is 50 minus 20. Now notice this is still an equal sign right here, yes? But since I don't have a graph made up of line segments or semicircles, nor do I have the equation of f, I can only approximate the integral. So this is where the squiggles come in, right? I have to approximate the integral by using the trapezoidal approximation. So remember, for the trapezoidal approximation, the 1/2 is always part of it, times the delta x, if it's uniform, can come out front, which it is. And now we add up all the y values and we double the ones on the interior. Yes, remember that? Yeah. So, and again, you don't have to do it this way. You could just do 1/2 the sum times the width plus 1/2 the sum times the width. But this expedites it. So it's going to be 42 plus. Now, again, if this were a free response, do I want to double 38 in my head and write it down as 76? No, because that's not going to indicate your method. So I'm just going to put 2 times 38 plus 2 times 31 plus 2 times 29. And see, I need to, I'm going to have to make more space here, right? Remodel. There we go. Yum. 2 times 29 plus 2 times 35 plus 2 times 48. There's the interior ones. And then plus 1 times 60, or just 60. Now there is the integral approximation, and I'll divide it by the width, which I'll just leave it as 50 minus 20, right? So if this were a free response, that's not a very satisfying answer, right? That doesn't really tell me what the average is, but it is an exact answer, and it does indicate your method. So this would be a 2 for 1. And now the actual evaluation of that number, although you want to take that, lightly, it's a moot point at this point, right? We're all assuming everyone can evaluate it and do arithmetic. So anyway, so let's say that we had this number and we had the arithmetic mean, which would be averaging them all and dividing by 7, or adding them and dividing by 7. Which one is better practice for this type of data? The trapezoidal. Very good, because the function is continuous. These numbers come from continuous data. Okay, so this will give you a different number than the arithmetic mean, but because it comes from continuous data, it's better practice. So, like I said yesterday, next time you're doing like a science lab and you're collecting like water samples or temperatures, and one of the questions is typically, what's the average of your data? If it's like from temperatures or continuous data, you might want to find it this way and see if Mr. Bowen or Miss Ortiz are like, okay, all right, I see where you're coming from. I'm not going to count it wrong, because they probably don't find it using the density method, right? And it's understandable. Okay, questions on that? Okay, sweet. While I've got y'all's attention here, I was going to make y'all's, I didn't make the meeting yesterday. I apologize. I thought it was at 7. I was at my dad's with the chainsaw clearing some of his trees. I was filthy at 6:45. I went home to take a quick shower, and that's when I saw whoever texted me. Was it Hank? It said it was at 6, and I was like, well, it's not worth. Yeah. So anyway, I didn't go, but it was at 7. Was it at 7? I went at 6. Oh. And they didn't make it clear. Okay. Yeah, miscommunication. 3 different starting times. Whoa. And Mason was at one of them and still didn't get his questions answered. If you have any questions about it, though, I do want it to be special for y'all. You can ask someone who knows. It seems like Ella knows a little bit. Oh, I wasn't in the cafeteria. Oh. And then at 7, they were going to piggyback it into the. I see. Okay. Okay, I got you. All right. Well, let's what I forgot where I was going with that. Yeah, but anyway. Let's do example 16. How about that? Thanks for the polite. Yeah. So anyway, it doesn't matter. Example 16, find the number. Oh, that's where I was going. Thank you. See, yeah, my brain, I'm not feeling so great here. Yeah, AP Classroom. I was going to do that this morning. I got sidetracked with an email. And so I don't have it yet. So instead of going live at this morning at 4:30, like I wanted it and having it due tomorrow at bless you at 4:30 p.m. I'll create it today during C lunch, and then I'll give you all the weekend to do it, like Friday and the weekend and Monday. We don't have school on Monday, so I'll just make it due. I'll make it due Tuesday. I'll make it due Tuesday by 9 a.m. Tuesday. Okay. Tuesday.
February 22nd.
Oh yeah, there you go. 222222222. All right. There you go. So now that's going to actually be better for me because I wanted to ask a question like this on your 5 questions. Okay. So look for that. We'll still have one, and good luck. Run fast, jump high, and yeah, breathe in the good air. Yes, Mason.
This is totally not this, but I'm so sorry.
No, it's all right. Hang on just a second. Hey, at least the bathrooms in this wing work. Hey, yeah. All right. Find the number of numbers b such that the average value of this quadratic that opens down on the interval from 0 to b is equal to 3. Okay. So now it's kind of like a variable setup. The integral divided by the width equals the average value. If I know the average value, but I'm missing any one of the other pieces, I can set up an equation, a conditional equation, and solve, right? So that's what we're going to do here. We could graph it to see what it is we're doing, but I think y'all have an understanding of what that is. So let's just go ahead and set it up by analysis, right? Instrumentation only. We're going to take the average value, and again, you can label it average value. In this case, it's the average f of x value. It's the integral of f of x from 0 to b divided by the width, b minus 0, and now we know it's equal to 3. Okay, so kind of like what we do when we set up the mean value theorem for derivatives, right? We take the derivative and we set it equal to the average rate of change. Here, we're taking the integral. Oh, I forgot the dx. Oops. Yep. See, that, Mason, would not have cost me a point. There's nothing. No, that would not. Because nothing follows it. There was no misinterpretation. Okay. But if it's in line with another one. Okay. So now let's go ahead and actually set it up. B minus 0 is b, of course. Dividing by b is the same as multiplying by 1 over b. So again, be mindful of that. When it's given to you as something to interpret, it's going to be given to you as 1 over the width out front. And now, since I have to actually work with this from 0 to b, I'm going to put the actual function in there. You would get a check for that setup right there, by the way. So now it's 2 plus 6x minus 3x squared dx, and it equals 3. All right, now how would you contend with the 1 over b out front? Well, it's a conditional equation. So would you multiply both sides by b? You certainly could. You certainly could. In fact, I think I'm going to do that. I'm going to multiply both sides by b. So now it's gone from the left and it's introduced itself on the right. Now I'm not going to show that. I'm showing it implicitly here because what I want to do is I want to integrate that now. I want to find the antiderivative. I don't want to do like just one little tiny thing per line. So now I'll integrate that, right? That's 2x plus 6 goes along for the right. It becomes x squared times a half. So we get 3x squared. Hopefully you're kind of doing this quickly in your head. 3 goes along for the right, x cubed times a third. They divide out, give you x cubed. All right. And again, the nice thing about anti-differentiating is you can check by differentiating. Yes. The derivative of what's in red should be in purple. And it is. Yeah. Very good. You don't have to bring the equal sign down on the left side anymore because what I've done is I've labeled this. This is a label. We have like f of x equals, it's a name function. So it's kind of like when I have f of x equals a function, and then I set it equal to 0. I don't have to keep bringing the f of x down. I take the name of it and I turn it into a conditional equation. Very good question. Yeah, I overlooked that, but that's important. Yeah, you don't have to bring that down anymore. And now I'm going to evaluate this from 0 to b. Okay, and I guess I can remodel. All right, so now it looks kind of funny, right? I need to solve for b, but I got x's and b's. Oh, but wait, the FTOC one, when I plug in the top gives me 2b plus 3b squared, right? A less famous Shakespearean line. Minus, when I plug in a 0, I get 2 0 plus 3 0 minus 0. Well, that's just 0. Don't always assume that just because you have a 0 as an interval of integration, whether it's lower or upper bound, that plugging in is going to yield nothing, right? You got to be careful. If it had been like e to the x, now e to the 0 would have been a 1. Okay, so notice now it's starting to look more and more like an algebra 2 problem, but with b instead of x. All right, let's keep going here. I'm going to red rover, let everything go over to the right side. Why the right side? Because my leading term is b cubed and it's negative. And I don't like to lead with a negative. That's why the tone of my first email is always polite. All right, so I bring that across and it's positive b cubed. And then it's going to be a negative 3b squared and a negative 2b plus the 3b that's over there, right? So all the signs change. And now I'm going to flip both sides. I do like the 0 on the right. So b cubed minus 3b squared. And of course, I can combine these. That's plus 1b and it equals 0. All right. Now I've got it down to a nice cubic polynomial. It's equal to 0. So what do we say? F it, right? Factor it. The first rule of factoring is pull out a common factor. So we do have a b, and that gives us b squared minus 3b plus 1. And that's equal to 0. And then we attempt to factor what's left. Oh my gosh. Factors of 1 that add up to negative 3. What? Oh, yeah. The product has to be 1. We want to make it work so very badly, but it doesn't factor. But good news, we have our handy dandy quadratic formula. Yeah. Are you allowed to use the quadratic formula in calculus? You shouldn't have to. All right. So here's a 1, here's a negative 3, and here's a positive 1. Those are my coefficients. Now, I will go ahead and set b equal to 0. That's one of my possible values. Okay. And then the others are going to be, well, the quadratic formula. B is going to equal. Now we got to be careful here because the quadratic formula has a little b in it, but the little b is the coefficient of the linear term. Right? So just think about it. It's the opposite of your linear term. So it's positive 3 plus or minus the square root of the linear term squared, which is positive 9, minus 4 times your quadratic term, which is 1, times your constant, which is 1, all over 2 times your quadratic coefficient. Wow. So now new column, I get b equals 0, or let's see, the conjugate pair, 3 plus or minus the square root of 5 over 2. Let's list those separately. B equals 0, 3 plus the square root of 5 over 2, or 3 minus the square root of 5 over 2. Holy crap. Right? It's a cubic polynomial. It has 3 solutions, and they're all unique. So they're all multiplicities of 1. Now, we got to answer the freaking question, right? That's the last thing we do. We're not just solving a cubic polynomial. We have those b values in the context of being what? Well, it's the upper bound on an interval that starts at 0, right? So what do we know about b? B has to be what? It has to be greater than 0, right? Because that's how intervals work. If b was negative, then what are you doing? 0 to backwards? No, that doesn't work. If b is 0, 0 to 0, why, that's not an interval at all. So we're looking for a positive value of b. Might there be more than one? Sure, maybe. Let's see. Let's come down here. Is 0 greater than 0? No. Is 3 plus the square root of 5 halves greater than 0? Yes. Is 3 minus the square root of 5 over 2 greater than 0? Maybe. The square root of 5 is 2 point something, right? 3 minus 2 point something is positive something. Positive something divided by 2 is positive. Oh, there's 2 of them. There's 2 different values. Wow. Wow. Is this problem a step outside of what College Board would ask on an AP exam? Yes. we shouldn't have to use the quadratic formula, but it gets lonely. It gets lonely when we don't use it outside of algebra 1, right? And then you get that tattoo on your forehead for nothing, or wherever you got the tattoo, right? Everyone gets the tattoo when they leave algebra 1, right? It's a rite of passage. It's like a branding iron. Congratulations, you pressed algebra 1. Here's your quadratic formula brand tattoo. Like on Yellowstone, where they all get the, never mind. Never mind. Never mind. There's two different values, okay? There's two different values. The quadratic formula. On Yellowstone, if you're part of the ranch, you're part of the group, you get a brand of a horseshoe on your chest, and that means that you're family forever. Yeah, so I thought they just branded everybody when you got it. When you finally passed algebra 1, they branded you with the quadratic formula somewhere on your body. Oh, there you go. Yeah, it's metaphorically. Okay. If this were an AP question, that quadratic would be factorable. Okay, and then you would still compare the values. You would still be looking for positive values. Okay. All right. Comments, questions. The idea is that what's important. How we set it up and what we're doing is important. The mechanics of it, the numbers itself, that's all algebra. That could be pretty much anything. Yes. Yes. Yeah. If it were a free response, you know, if you cross out the 0, it's gone. And then you can leave the other 2 as a conjugate pair, we call it. Yeah. All right. Sweet. Here's something that's kind of in the same lines, but you don't have to set up the equation. It's already set up for you. So this isn't average value necessarily more. This is just a conditional equation that involves a definite integral. All right. So let's look at this one. Solve for x. That's what it's going to say. It's going to say solve for x. So if you look at it, it's the integral from -5 to x. Oh, there's your variable of some other variable, t cubed minus 7t with respect to t, or p cubed minus 7p with respect to p, equals 0 for x. Now, you could do this one of two ways. You can just set out, you know, using analysis like we just did, let the algebra do the talking, or you could try to make sense a little bit of what's going on graphically. Okay. Let's try to make sense at first of what's going on graphically. It's not a requirement, but it is a good review. This is your integrand. So if you go off to the side and you let that equal y, or let's let it equal f of t. How about that? We'll give it a name. It's t cubed minus 7t. Is that it? Are we done? No? Oh, we got 30 minutes more. Oh, go. Good, good, good. What do I know about this function? I know it's a cubic polynomial, right? It comes in the bottom, it goes out the top. I want to find the x-intercept. So let's set it equal to 0. And again, now we'll factor it. And as Angelique kind of noted earlier, now that we've made it into a conditional equation, we don't need to carry down the equal sign on the left-hand side that named it. And look, t squared minus 7, it's a difference of 2 squares, right? Not 2 perfect squares, but 2 squares. So you could either say t equals 0 and then just rattle off the other 2, or you can actually set them equal to 0 and factor it, or separate the variables and extract both square roots, but they're going to be plus or minus the square root of 7. Okay, now these are just the x-intercepts of the function. What that's going to allow me to do is sketch the graph, right? Here's negative root 7. Here's positive root 7. Here's 0. It's a cubic polynomial, so it's going to come in here, turn around there, come in here, turn around there. Does this function graphically look like it has any symmetry? Yeah, it looks like it's a what type of function? Odd function with origin symmetry, right? That's your rotational symmetry. Now, we could have verified that algebraically up here. If you replace t with negative t and separate it, since both terms have odd powers, both signs will change. If all the signs change, it's odd. If none of the signs change, it's even. If some change and some don't, it's neither. So this equals the opposite of f of t. All the signs change. So you could have spotted that symmetry to begin with. The more you know about a problem going in, the easier it is for you. Because now we want to find the integral from -5. -5 is over here to the left of -7. I want to know from -5 to what value of x is the net accumulation 0. Well, because we know what the graph looks like now, you should know two values off the bat. Let's list two of the x values. What's one x value for sure that we know is going to give us a net accumulation of 0? Negative, not negative square root of 7. What happens if you don't go anywhere, let any time expire? You won't accumulate anything, right? Nothing ventured, nothing gained, right? In other words, the integral from a to a of any function f of x dx is equal to 0. Nothing ventured, nothing gained. You haven't let any time go by to accumulate or lose anything. You can think of it as area as well. The width is 0, right? So I know x equals -5, but because it's origin symmetric, I know that in this case, x could equal 5. And now I'm going to have equal areas and magnitude, but opposite signs. Symmetrical intervals for odd functions also nullify each other. So that's two of them, right? Now, might there be another? Well, let's see. Think about what we're doing. We're starting at -5. As I integrate from left to right, I'm accumulating negatively, right? I'm losing. Might there be a point then, as I cross at the square root of 7, might there be a point, mind you, this is not drawn to scale. Might there be a point somewhere here before 0 where I zero back out? I lose something and then I gain some back. Could I zero out there? Possibly. Now, it could also be that the region below is larger in area than the region above, and I never quite get back to 0. But if that is the case, and I did zero out there, now I would have like a little sliver more of positive, and then a little sliver of losing again. There might be another one there, right? Perhaps. And then after that, I'm in the hole again. And then there might be a place where I zero back out. So there might be like two more values on the interior. I don't know. Or it could be that there's none. But I do know that -5 and 5 work. So that's not going to necessarily give you all of them, because if there are any on the interior, you can't really tell qualitatively. So now it's time to bust out the calculus, okay? Which you could have done from the very beginning. All right, but it's always nice to visualize what we're doing. Okay, so here's what BOTCing looks like. Let's find the antiderivative with respect to t. 1/4 t to the 4th minus 7/2 t squared from -5 to x, and we keep it equal to 0. It's a conditional equation. I plug in the top, and I get 1/4 x to the 4th minus 7/2 x to the 2nd. I plug in the bottom. Ay, caramba. Caramba. Ooh, is this going to be fun? Possibly. -5 to the 4th. Well, that's -5 times -5, which is 25. 25 times 25, 25 squared, 625. Very good. Oy, right? Minus 7/2 times t squared, that's -5 squared, that's 25. Boom, boom. Right? So again, remember, bless you, plug in the top in parentheses, minus plug in the bottom in parentheses, and that equals 0. All right. Yay. The calculus is over. It actually lasted one line, really, but if you think of evaluating using the FTOC, it actually lasted 2 lines this time. But now it's time to just use good old-fashioned algebra. But we're not in honors algebra anymore. We're like in super deluxe AP honors elite algebra, because you never saw numbers like this in your algebra class, right? And that's what calculus is. It is super deluxe honors elite extra algebra. So let's go ahead and simplify. I'm going to drop down these parentheses, right? Tear down these walls, Gorbachev. No, that's supposed to be Ronald Reagan at the Berlin Wall. Right. JFK at the Berlin Wall is, hey, I'm a jelly donut, right? Right, yeah. You can Google that too. Okay. So 625 divided by 4. Does 4 go into 625 evenly? I don't think so. So I'm just going to call it, look, I'm just going to call it 625 fourths. minus 7 times 25. If I have 7 quarters, how rich am I? Very rich, right? I've got 175. Yeah, cents, centavos, right? Times 2. Uh-oh, I better get a common denominator inside there. Maybe. You know what? Forget this common denominator crap. Raise your hand if you want to work with the fractions. That's what I thought. No one raised their hand. Oh, no. I gave y'all too much time. Let's clear out the fractions, shall we? We're going to multiply. It's like the lick 'em over lick 'em, but instead of the expression version, it's the equation version. It's lick 'em on one side and lick 'em on the other, right? So what is the LCM of all of my miniature denominators? 2 and 4. 4. All right. So we'll multiply this side by 4, which Hank knows all about 4. When he's on the golf course, he gets hoarse yelling that on the course, right?
And then I aim for Coach Bear and I whisper it.
Oh,
Geez,
oh, nice. Good one.
Coach Bear, catch.
Catch, right? Play catch with me, Coach Fair. All right. Now we'll carefully distribute. We get x to the 4th. That's good. Minus 4 divided by 2 is 2. 2 times 7 is 14. X squared. And then I'm going to distribute the negative and the 4. Is that okay? I'm distributing a negative 4. It's super deluxe extra algebra, right? So I get negative 625 plus 4 divided by 2 is 2. What's $1.75 plus $1.75? How rich am I? $3.50. Oh yeah, the 350Z. That's a nice automobile. Hey, let's combine like terms now. I'm no fool, no siree. I'm going to live to be 103. If I don't read any more emails, my stress level will go down and my heart will be happy. No, yeah, well, I mean, from you, it's okay. From you. All right. Just make sure that the topic says in the subject line, donuts, right?
Or suits.
Or suits. Suits. Oh, yeah, the show suits. Not like double-breasted single. It's the show. Yeah, I get it. Okay.
Yeah.
What's negative 625? You owe me $6.25 and you pay me back $3.50. Yo, you still owe me how much? You still owe me $2.75. Okay. And I'm going to get it from you. Don't think that I'm going to forget. All right. Now, hey, look, all this hard work gets us down to here. Look, this is a 4th degree polynomial. It can have up to how many solutions? 4. We already know 2 of them, don't we? And we said that there could be possibly how many more on the interior? 2 more, possibly. Now, if you're trying to F this, right, factor it, you can either like say, okay, it doesn't matter if it's x squared and x or x to the 4th and x. I mean, x squared and x, as long as the larger degree is twice the smaller, you could factor like you normally would. Now, this could factor into x squared plus or minus something times x squared plus or minus something. Your target product is negative 275. Your target sum is negative 14. So if you get no help, you're like, man, what are the factors of 275 that add up to negative 14? Let me consult my crystal ball right here. Nah, it's eluding me. It's eluding me at the moment. But if you're like, hey, I already got some intel, right? I got some insider trading info. These 2 guys, when you plug them in, gives you 0, right? So remember, if you know a factor, you know a root. And if you know a root, you know a factor. And if you know a factor, you know a root. But in this case, if you know a root, you know a factor. Yeah, yeah. So let's come over here and say, all right, if negative 5 is a root, then x plus 5 is a factor. And if positive 5 is a root, then x minus 5 is a factor, right? Now, if I expand that out, that gives me x squared minus 25. Hey, maybe that's one of the factors down here, x squared minus 25, right? I don't got to reinvent the wheel, right? When I want to drive a car, I just get to the car and I'm like, oh, this already got wheels, right? I just get in and drive. Boom, right? Now it makes it easier. This has got to be another x squared. I don't know why I'm talking like this, but it seems right. Negative 25 times a what gives me a negative of 275. How many quarters it take to get $2.75? 11? Well, let's see. Well, you know, that's why I never lending you money. You're bad with money. I think it's 11, right? So it's got to be what? What type of 11 here? It's got to be a positive. Now, all we got to do is check. We just got to check. Negative 25 plus 11 is what? Negative 14. Boom, we got it. Boom, we got it, right? Now that we got it factored, now we can set each factor equal to 0. Either x squared minus 25 equals 0, which we know x equals plus or minus 5, or x squared plus 11 equals 0. Ha! Right? Ha! That's like getting Hank to pay me back the right amount, right? It ain't going to happen. Right? Bad with money. Is x squared plus 11 ever 0? No. It's got two imaginary roots, but hey, you know, I'll lend you imaginary money maybe, right? Pay me back tenfold. So, hey, it could have had two more roots, but does it? No. So, wow, it turned out that the two that we had in the beginning from our algebraic efforts were the only two. So some people, bless you, might look at this and say, then what do we do this for? We had to do it because we didn't know that there were not two more until we discovered that there were not two more, right? Qualitative analysis is only that, right? You got to quantify it. The numbers don't lie. The numbers don't lie, which is why you could trust the numbers. All right. How does that feel? That feel pretty good? All right. So I'm not going to do this one here, but tell me right away what a solution is. I want to find a K value now that gives me a net accumulation of nothing. Will -3 work? Yeah, it's got to work, right? The integral from -3 to -3 is nothing, right? We didn't go nowhere. We didn't do nothing, right? Now, is 3 also a solution? Okay, that'll make a good answer choice. Note to self, bait in Hank with an answer choice of 3, right? I don't know. Let's look. X squared minus 4. Here's -4. Ay, caramba. Ay, caramba. Here's -2. Here's +2. Here's -3. Is this an odd function? Does it have origin symmetry? No, no. So does that work for even functions on symmetrical intervals? Not in general. Not in general. So it might not be, but it still might, right? Watch this. As I go from left to right, I'm gaining, right? I'm getting stuff, but then now I'm losing, right? Now I'm losing. Now maybe those equal out. Maybe those are equal right there, right? Maybe. And if so, now I'm losing some more. And now maybe I gain back just at the right place at 3, maybe, right? But it's not a gimme, right? Bless you. There's nothing there qualitatively that tells me it's got to be 3 because there's no equal but opposite going on. So I know -3 is a solution for sure. After that, I got to do the analysis, and I'll leave that to you to do in the privacy of your own home. I don't want to see that, right? Behind closed doors, keep it there. All right. I don't know why I'm talking like this. I don't know. I don't know. I just feel tougher, you know. I feel tougher. Like the math doesn't even got a chance against me today, you know? Right, Paulie?
All right, that's right.
All right. All right. All right. Any comments or questions? All right. Let's move along. Hey, how many examples this year have we come across that have had the all caps words important in front of it? Yeah, this is the first one, right? This is the very first one, right? Natural log of 1, right? We've had that many. This is the first one. So, man, this must be what's the word I'm looking for? It must be important. Yeah, it is. This one idea right here, and I can put now questions on those AP 5 questions that are this. This one idea right here is pretty much all of section 6.3. It encompasses the entire theory behind net accumulation. Okay, net accumulation. Yeah, we ain't even at 6.3 yet. But if you understand this example, we probably skip 6.3. All 6.3 does is it does this kind of stuff with units, right? Like sewer is accumulating in a school hallway at a rate of, right? If there are, 52,000 gallons of sewage in the 200 wing at time zero, how much sewage is there at the end of the day, right? That's a true story. Oh yeah, I wasn't kidding when I said at least the bathrooms over here work. The bathrooms in the other part of the school, they don't work. There was raw sewage in the 200 wing yesterday. Yeah, towards the end of the day. Yeah, we had some plumbing issues. Yeah, yeah, yeah. That's what we're talking about, right? Okay, so let's get back to important example 18. Indoor plumbing is important when it works. Probably even more important when it don't, right? Someone call the plumber. Ready? All right. Net accumulation. Now, here's what I want you to read. We're going to skip that example. We're going to preface it by coming down here. Right? Hard facts to refute. If you want to refute it, come at me, bro. Okay, we'll try it. Hey, try to refute this, if you will. Right? Hey, where you are at any given moment. Right? Are you with me so far? Yeah. Where you are at any given moment, it depends on, or it's a function of two things, right? And refute it if you might, right? You're gonna fail. Where you started, right? Your starting point, and then where you've gone since then, right? You tell me those two things, I tell you where you are, right? Right? Yeah. Like, hey, yo, Mr. Corbett, I started at the bottom, and then I started working with you, and now I'm at the top, right? Yeah, that's right. That's right. Yeah, I'll take you places, right? No, if you just tell me where you've gone from your starting point, I won't know where you're at, right? Like if Hank texts me and says, "Yo, Mr. Corpy, hey, an hour has passed since I last texted you. Guess what? I've been on I-35 the whole time, but now I'm like 50 miles north from when I last texted you. Hey, guess where I'm at?" And I'd be like, "I don't know. Are you in New Braunfels? Or are you in Rochester, Minnesota? I don't know. Are you in Wichita, Kansas, which is where I-35 turns into a freaking toll road? Like, that's not fair. I don't know. I have no idea, right? I need to know where you started. And then you're like, oh, you started in New Braunfels and now you're 50 miles. Oh, hey, you're like in the Austin area. Like, how did you know? And I'm like, it's a gift, right? But if you just tell me where you start, Mr. Corpy, hey, guess what? I was in Cotulla an hour ago and now I'm not. Where am I? I have no freaking idea, right? I don't have that app that tells me where you are on the phone, right? My wife has it for the kids and for me, I guess, but I'm Android. I protect myself. I don't know where you are. You tell me you're in Cotulla, you could be in Timbuktu, I don't know. But if you say, hey, I was in Cotulla and now I'm like 200 miles south, I'm like, you're at the border, aren't you? You're going into Progreso, Mexico. Yeah, you're going to get some diesel fuel for 7 cents a gallon, right? Half diesel, half water. Yeah. That's what I used to do growing up in Weslaco, Texas. All right. So you have to know both pieces, right? You with me? Where you are at any given moment is a function of your initial position plus your displacement. Since that time. Yeah. Now, we don't have to be talking about motion. We could talk about like material possessions, right? That's what life's about, getting as many of those as you can, right? All right, let's read this. Part B, come at me if you want to. What you have at any given moment, what you are in possession of, whether it's an iPad, frustration, or raw sewage, right? What you have at any given moment is a function of A, or number one, what you started with, plus number two, what you have gained / lost, or we call that accumulated since then, right? Right? I went to Vegas. I had 50 cents, right? And I was playing nickel slots for like 5 minutes. And now I lost my 50 cents, right? What do I have now? Well, 50 plus negative 50, you got zero, right? You're zero. You got zero. But hey, I started with 50 cents and then I played a nickel slot. And on the very first pull, I won $2, right? Now you're like, oh, okay. You have 45 cents plus $2. You got $2.45. You might as well quit while you're ahead, right? Get out of Vegas while you can. Take the money and run. You can't just say, hey, guess what? Guess what? I won $2. How much do I have now? I'm like, I don't know, but you owe me $2. So now you have nothing. Give me that and everything else, right? Or you could say, hey, I went to Vegas with 50 cents and I gambled. And guess what I went home with? No, we're not playing that game. No, you tell me, and I'll tell you, right? What the heck does that have to do with example 18? Well, it's the important idea of accumulation. Look how many asterisks we have here. That's a lot, right? Now look, now I have one of these asterisks means very important. One of them does. So look how many we have. Don't count them. It'll make you cross-eyed. Here's we go. Look, so look, what I have now, whether I'm collecting money or position units along I-35, is what I started with, either in dineros or miles or gallons or emails, plus what I've accumulated since I started. And accumulated is net accumulated. It could be gained or lost. Gain and or lost since then. Okay. Here's how we could state it mathematically. F of B, that is the function value at time B, is equal to F of A, your starting value at A, plus your net accumulation from A, where you started, to B, where you're trying to get to, of your rate equation. Okay, that's it. If you just take the integral of f prime, you're going to get the net accumulation. Okay, but when you add that to what you started with, you get the current amount. All right, does that make sense? This piece here is your net accumulation. This is your starting amount. And this is what you have now. All right. It's kind of like your position now is your initial position plus your net accumulation of position units using the rate equation, which is velocity. All right. Let's come back now and look at example 18. If f prime of x is equal to 2x squared minus 2, and f of 0 is 5, find f of 2 by finding the particular solution to the differential equation. All right. We can answer this right now by going back to 4.1. Let's do that first. This is a differential equation, right? How do I know? It's a derivative with an equal sign. I want to solve it by getting back to f of x. I have an initial condition, right? I have a point that satisfies the previous function. So we'll call this method 1. We'll call this method 1. This is using section 4.1. We're going to say then that f of x is the antiderivative of 2x squared minus 2, which is 2/3 x cubed minus 2x plus c, right? This is what we call the general solution. Yes? All right. Now we could say at the point 0.05, or for f of 0 equals 5, I'm plugging in. We get 5 equals 0 minus 0 plus c. So c equals 5, right? And now uniquely we could say, so f of x must be 2/3 x cubed minus 2x plus 5. And this is what we call the particular solution. Particular in that it's the only function in the whole wide world whose derivative is 2x squared minus 2 that happens to have a y-intercept of 5 that passes through the point 0.5. Okay. And now that I have the function, I could evaluate it at any other x value that you give me in the whole wide world because it's a polynomial. It's continuous and defined everywhere. Oh, you happen to want f of 2? I'll oblige. Here we go. F of 2 then must be 2/3 times 2 cubed is 8 minus 2 times 2 is 4 plus 5. And if I simplify, I get 16/3 plus 1, which is how many thirds? 19/3, right? 19/3, which is also equal to what? 6-point forest, right? Oh, yeah. Tree, 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 tree. Boom. See if that catches on. Not a problem, right? We can do it. We did it. We did it, Lois Emos. No problem. In fact, it was not a problem for one particular reason. We were able to find the what? The antiderivative. This method relies exclusively on knowing how to find an antiderivative. Will we always be able to find an antiderivative? No. So method 2 will have to wait till tomorrow. This is such an important section. We don't rush it. Not yet. This is motivating you to what we are going to do using the important idea. But like the Yankees under Stengel, they never lost the game. They just ran out of time. As well today we have. Okay. Tomorrow I'm going to show you method 2, and it's going to involve a definite integral. Because here's the bottom line. If I can write that same problem as a definite integral, now I can write a program to do it numerically. So that when we're too lazy to find an antiderivative or the antiderivative can't be found, we can still let computers find it like your TI-84s do, numerically. And that's the important idea. All right. Remember, where you are at any given moment is where you started, plus your net accumulation since then. Right now, you're starting in room 903. And then from here, for y'all, it's only up, right? Only up in all directions. Right, Tony? All right. All right. We be done for today.